Thanks for joining us. I'm Steve Hsu.
And I'm Corey Washington, and we're your hosts for Manifold. Our guest today is Dr. Klaus Lackner, Director of the Center for Negative Carbon Emissions at Arizona State University. Dr. Lackner is a pioneer in the field of carbon management and was the first person to suggest capturing carbon dioxide from air as a means of addressing climate change. His research and inventions have demonstrated the feasibility of carbon dioxide removal and integrating air capture technology with downstream uses of CO2, in addition to exploring safe and permanent disposal options for CO2. He co-founded one of the first privately held air capture companies, and his patented technologies have formed the basis of a number of other companies working in the field. From 2001 to 2014, he was director of the Lenfest Center for Sustainable Energy at the Earth Institute at Columbia University. Prior to his academic work, he held appointments at the Theoretical Division of Los Alamos National Laboratory for nearly 17 years. Welcome to Manifold, Klaus.
Thank you.
To begin, can you explain to us what is carbon management?
Well, we use energy in very large amounts, and more than 80% of the energy we consume comes in some form or another from fossil carbon. And an unfortunate byproduct of combusting fossil fuels is that they all end up producing CO2, which we happily dump into the atmosphere. And just like we need to manage waste, we will also have to manage the carbon we are putting out into the environment, because we are overwhelming the ability of the environment to actually hold that extra carbon.
So when you speak of carbon management, you have in mind a sort of determinate policy of controlling how much is being put into the atmosphere and how much is being taken out?
Right. The way I'm looking at it, in many ways, it's a waste management problem. We are producing carbon from underground, which has been safely put away from the surface environment for millions of years. And in rapid succession, we take that out. And one of the things which motivated me early on was the observation that at least half of that CO2 sticks around in the atmosphere for many, many centuries, if not millennia. And we have completely overwhelmed natural sources of carbon entering the surface carbon pool. And as a consequence, we are dominating it. We are now have pushed the CO2 in the atmosphere from 280 parts per million, where it was at the beginning of the Industrial Revolution, to about 410, 412, and it's going up at about 2.5 parts per million a year right now. So if 450 is sort of a critical boundary where people talk about that's sort of the limit we should stay below, well, we are by now 15 years away from that.
You've been described as the first person to suggest pulling carbon out of the atmosphere as a way of addressing climate change. And I have to say, I find that kind of remarkable because it suggests that we've been pumping this stuff into the atmosphere for a long time, and it simply never occurred to anyone that we might want to take it out. Is that simply because it was never thought to be feasible until a certain point?
Yes, I think the biggest issue is feasibility. And then for the longest time, people didn't think it's all that much of a problem. Right? You have a fire and it produces CO2 and it dilutes itself in the atmosphere. If you go back to the 1960s and 70s, there was even in environmental engineering, the paradigm dilution is the solution to pollution, right? And at some point we figured out that the atmosphere is simply not big enough to dilute it. And unlike sulfur dioxide or nitrogen oxides, the CO2 does not go away by itself, because the natural processes, the geological processes which remove it from the surface carbon are so slow that it will take thousands, if not hundreds of 100,000 years for this equilibrium to be reestablished. So in the meantime, we have to deal with it. And in a way, it's not all that different than sewage was in the 19th century. Even the discussion is similar. A little bit of slop hasn't hurt anybody yet. And you can't prove that it has any impact on health. So just live with it. And then eventually we could demonstrate that typhoid and cholera are directly related to it. And suddenly it became feasible to run canalization, run channels under tunnels under all the major cities in the world and take care of that sewage.
So, Corey, I don't want to hijack from your outline on this episode, but Klaus, I want to ask, so are you pursuing this line because you think there's some tail risk of a catastrophic outcome from further increases in carbon levels, or are you somehow absolutely sure that there will be a catastrophic outcome?
I mean, the tail risk is obviously an important thing to consider. On the other hand, what convinced me early on was the simple observation: the CO2 goes up and it stays up. So you can argue long and learned discussion. What is the limit you can go to? In the early 90s, when I got started, I sort of took the point of view, I'm a dumb physicist. I don't really know what will happen, but anything which is physiologically, from climate change perspective, important, I don't really want to double. So I naturally put a level and say 550 is probably the limit. And you could back then see, if you follow business as usual, we crossed that line sometime in the early part, middle part of the 21st century. So it was absolutely clear to me that the world had less than a century to figure out how to go from an energy system that's carbon dominated to an energy system that is carbon neutral. In the meantime, the climate science has moved forward, and by now people say we probably should stop somewhere between 1.5 and 2 degrees. And if you take the 1.5 degrees seriously, that's probably below 450 ppm in the atmosphere. It depends a little bit on the model. So to me, by now, that's in the rearview mirror. Not quite yet, but we have enough momentum that we will pass the 450 mark. There's no question. So my tune has changed in the last 5 to 10 years from saying we got to stop to we will also have to mop up what we already have put out. When you had asked me in the late 90s when I started to work on air capture, I would have said the reason we need it is because we have airplanes, we have lots of distributed small point sources where we can't practically collect at the point source. And if you want to deal with them, you better have an ability to pull the CO2 back out of the environment, and air capture is a good way of doing this. By now, I'm going to tell you that's all fine, but besides, we already have to deal with past emissions. And I'm arguing now we probably have an overhang of about 100 ppm, and I'm still agnostic what exactly this means. Will we go to 500 ppm and come back to 400? Will we come back from 450 to 350? But order of magnitude, we are now in a carbon debt. We have excess on the order of 100 parts per million, which turns out is the equivalent of about 1,500 gigatons of CO2. And that means we have to collect more CO2 back than we emitted in the 20th century. But right now it takes us about 40 years to do that.
Okay, I don't want to belabor the point, but many people would say that setting a particular value like 450 or 500 and claiming that the actual consequences for the environment is fraught with lots of still large uncertainty.
I'd be the first one to admit that.
Right.
On the other hand, if you don't do anything, we'll be at 1,000 ppm before the century is out.
Right.
So you pick your number, and I don't think anything magic happens at 450. It just gets progressively harder, right? And clearly, if when I started to think about it in the early 90s, climate change was something for theoreticians. I could sit down and work out the warming potential, and I can give you simple physics models which tell you that it will get warmer. But I would have to admit in 1990 or 1995 that, yes, I can theoretically see it, but of course the natural noise in the system is so large that I haven't seen it yet. If you go to the early 2000s, you can see the IPCC basically saying you have good instruments, you can measure the change, and it is by now clear that the anthropogenic component of warming is clearly visible if you pay attention and you have the right instruments. If you go to the last decade, which just ended, you can honestly say that climate change is now visible to most people. We can argue whether it's harmful or not, but it clearly has gotten warmer. Rainfall patterns have changed, and the ice in Greenland is melting. You can't argue with that anymore. And on the other hand, I would argue the last decade, the size of these effects was comparable to natural fluctuations, but it put a definite bias in one direction.
Mm-hmm.
I think this is still growing, and so it will become louder. And I think this is the decade where the stuff really comes out of the ground and becomes truly visible. So in an analogy, in the 90s, you had seeds in the ground and you know they were there. If you look carefully, there were weeds between the corn and the 2000s. And whatever weeds you had in the last decade were comparable to the height of the corn. This decade, they will be bigger. Right? And so we can argue long and forth what caused the big fires in Australia, what caused the fires in California. And surely these first things which hit you are always a combination of things, because it's the peaks which get you, and the peaks tend to have multiple causes because that's what got you there. But that drought and climate change have contributed to that, I think, is no question. And so we can argue whether this is just a cost, and at some point that cost is higher than the cost of fixing it, or whether this is cataclysmic and catastrophic and will end life the way we know it. I think the likelihood of that is not high. On the other hand, I would also argue, and we tend to underestimate that, we're not good at transients. And somebody once explained climate versus weather to me, and I thought that was very insightful. He said, weather is something we dress for. Climate is something we build for. And if we built the wrong infrastructure because the climate changed on us, this will be very, very expensive. You could have a climate where you are as hot as Phoenix, and it would be absolutely disastrous for you. It's not disastrous to us because we planned for it. We have built it like that. And if you had 110 and no rain for 3 months, you'd be in trouble because your infrastructure is not built for it. If it turns out there's a dramatic change in the climate, you will have enormous reinvestments into infrastructure, and those need to be paid for. My view when I got into this was actually not so much the climate debate. My view was we need energy, and our energy is tightly coupled to the production of CO2. And even today, more than 80% of all of our energy resources are fossil in nature. And so it's then just a matter of time that we have to get carbon neutral. And my concern was, how do we get carbon neutral, given that we don't have all that many options? So if you look at what I wrote in the late 90s and early 2000s, I made the argument that we basically only have 3 big energy sources, which are big enough to satisfy the needs of a 7 to 10 billion world population, which strives to have a standard of living like we have today. So energy consumption is presumably much higher than it is today. And back then, I would argue it could have grown tenfold. We probably doubled since then. So part of this we got, right? But if you look at it from that perspective, you only have nuclear energy or fossil energy and solar energy, which are truly large enough to deliver that. And back then, I would have said all three have rather serious issues. The carbon dioxide from fossil, you cannot accept indefinitely, so you have to figure out how to make that world carbon neutral in spite of it. And that's what got me to carbon capture and storage and sequestration and all of that. Nuclear, I felt, had three big problems. One is, and it still has that today, it's way too expensive. We have not managed to get nuclear energy cheap. Secondly, it has a safety and a security problem, right? The safety problem, we have by now had three major blowouts, and they are awkward for a nuclear power plant. And we have a serious proliferation issue, which we haven't really solved. So that is still in the balance. And after Fukushima, nobody wants to talk about it anymore. So in a way, this one derailed, right? But it could come back in a decade from now, who knows? But then the third one is solar. And back then I would have said it's too expensive and too intermittent. And I think the too expensive has been resolved since. But I would argue, I can think of a lot of other energy sources than those three, but I can't think of any other which actually can operate at the scale we need, right? We are consuming 17, 18 terawatt of primary energy, and tidal energy on the planet is about 3.5 terawatts. Wave energy on the oceans is around. The power in wave energy is around 4 terawatts. And wind energy is big enough, but if you were to really pull that much wind energy out of the system, you are going to change the climate as well. So you are left, and hydroelectricity may be the cheapest energy around, but there's clearly not enough for the planet. So we are stuck with those three, and I argued consistently that we need to place a big bet on all three and hope that at least one of the three bets pans out, because if none of them work, we are in real trouble.
Right. So I think, if you just say fossil fuels could end up being our main source of energy for quite some time, then at some point you will really care about pulling carbon out of the atmosphere, right? So that's enough motivation.
That was my original motivation. But if you simply now see the development, take the IPCC, take it what you see, right? If you look at the events in Australia right now, or if you look at Harvey, right, those things were predicted. Now, can I tie an individual sequence of events to that? Not really. On the other hand, it is what you expect. And so consequently, it's not unreasonable to assume that we start paying a price for all of this, and human dynamics will tend to enlarge those costs.
Now, just getting back to solar, so you mentioned that the cost is really not the issue now, but intermittency is the issue. So maybe battery technology has to improve quite a lot. But for your purpose of pulling carbon out of the air, the intermittency isn't really a problem, right? So is the vision
No, as a matter of fact, I see two major reasons to have direct air capture. One is the waste management approach, and I am arguing that you probably will have to clean up the last 50 years of emissions. Think of 100 ppm, and that needs to be stored. But the question is, where do you go in the future? And if solar energy becomes cheap enough, think PV, then you could take advantage of it in spite of the fact that it's intermittent, and make hydrogen. Mm-hmm. So your first step is to electrolyze water to make hydrogen. And if I give you CO2, between the two of us, we can now make any liquid fuel you like. So I could have an extreme version of this where and this is hypothetical and a thought experiment, so don't take it too seriously. I don't want put PV on the grid because it just upends the system because I can't predict when it's on and off. So instead, I use that energy, which is gradually getting down to a penny a kilowatt hour, to make hydrogen. And if my electrolyzers get cheap enough, I can afford the fact that they are not running 24/7, but only 1/3 of the day. And now that I have hydrogen and CO2 from direct air capture, I can make synthetic fuels. I could very well see a future where methanol as an intermediate product has about the same cost as a barrel of oil per unit of energy has today. So then you could say, well, let's see what we can make out of it. We can make jet fuel, we can make natural gas, we can make all of these things. And to begin with, we could do it exactly in the ratios we do today. So you could maintain your existing infrastructure, except that you didn't use fossil anymore, and the system moved forward. Now, was that optimal? Of course it was, right? Some of the electricity should go straight into the grid. Some of it, if you only wanted to store for a couple of hours, the battery is clearly better than making chemistry and then come back, because you can get 80% back of your energy, or 90 maybe even, if you ran through a battery, whereas you lost 2/3 of it if you went through this cycle. On the other hand, if you want to even out seasonal variability, batteries will not likely to be cheap enough for this. So I have a rough rule of thumb. If you invested $1,000, you better make a penny an hour. And batteries right now are maybe, what, $250 a kilowatt hour capacity. So if you empty that thing once a day, you're talking 6 cents per kilowatt hour. If you do it once a week, you're talking 40 cents a kilowatt hour, just for the privilege of owning the battery, right? If you decide to run a seasonal cycle, so you do it once a year, you're talking about $20 a kilowatt hour. Now, surely this will get cheaper, but $20 is an awful place to start with. So I see that short-term battery storage is very nice in batteries. Long-term storage is not so much. And if we with air capture are competing with anything, it's actually batteries in vehicles, right? Because if you didn't have a CO2 problem, because the carbon came from the air to begin with, what's the big deal of having liquid fuel in the car, right? And so you could very well have synthetic fuels for that. Cars may go electric anyhow, but somewhere is a boundary. Heavy trucks are probably like liquid fuels. Airplanes are very hard to run on batteries, except for very short hops, because a battery is about 100 times as heavy per unit of energy than gasoline or jet fuel. So I could very well see a world which is 100% solar, 100% renewable, and still is using large amounts of carbonaceous, carbon-based liquid fuels, but provides them from carbon that's basically from the ash, from CO2 and water, which it converts back into hydrocarbons with the energy of a solar panel. And so you could run where you live or in Boston all winter on a gas-fired power plant, where the energy from that gas has been produced somewhere in West Texas or in Arizona last summer, right? And you can literally store a gallon of gasoline for a couple of years without running up a bill.
So, sorry if I've messed up your agenda, but Corey. But so one question I have is, maybe you could walk us through the basic physical mechanism for carbon capture, the level of efficiency, how much energy you have to put in to capture each ton of carbon from the atmosphere.
Well, it's actually fairly straightforward. When I started with this, first thing I noticed is that CO2, not surprisingly, is very dilute. 400 parts per million says there's one molecule and 2,500 is CO2. So clearly you cannot spend much effort on the air itself, because anything you do to the air is amplified 2,500-fold relative to the CO2 you have, since you only get a fraction of it. the multiplier may even be worse. So you cannot heat the air, you cannot cool the air, you cannot compress the air. Blowing it around is already marginal. And I said, well, if I give myself a 50 kilojoule per mole budget, how fast can I move the air? I can get to about 10, 15 meters a second. If I go faster than that, I already blew my total energy budget. So I concluded, if I'm not much faster than the wind, why not run it like a wind energy system? And that actually was what motivated me to begin with. Back then, being a physicist, I did it in energy units. Today, I do it in economic units. So I'm saying a cubic kilometer of air runs through a windmill, and you can work out these big windmills you have nowadays in an afternoon, have seen a cubic kilometer of air. How much kinetic energy is actually in there, and I'll give you 6 meters a second to have a number. And there's about $300 worth of kinetic energy if I value kinetic energy at 5 cents a kilowatt hour. So that's what you have. If I'm willing to pay you a tipping fee of $30 per ton of CO2, I can now ask the question, how much CO2 is in that same cubic kilometer? And it turns out it's $21,000, 70 times bigger. Back then, I did it in energy relationship, and I said, well, I have the kinetic energy, that's energy, and I value the CO2 as the ash of a combustion process, and that's 700 kilojoules per mole of CO2 if I burn gasoline. So I can now ask how much CO2 in units of joules is in a cubic meter of air by that conversion, and that then the factor was 500-fold. So in a way, I convinced myself very early on, if we can afford windmills, we can afford passive devices standing in the air collecting CO2. And not knowing anything at the time, I said, well, assume for the sake of argument that my contactor has the same cost as a windmill per unit of area, per unit of wind seam. And I came to the conclusion I can contact the air for 50 cents per ton of CO2 if I cost the same as a windmill and have a comparable efficiency. So my conclusion was, if I'm passive and stand in the wind, my cost is not in contact. My cost is in the second step. Now, the second step, I need to bind the CO2 to something. And the question is, what do I bind it to? And any sorbent you have, either chemically or physically, attaches the CO2 and releases energy in the process. So standing out in the wind, I actually don't consume any energy. I'm binding CO2. And after a certain while, my sorbent is filled with CO2, and now I need to get it back off. Now I have to put the energy in, the binding energy back in order to push it off. So I can now ask, how much binding energy do I need to have? And that gets you to the thermodynamics, and after some back and forth calculation, you can conclude that at a minimum you need 22 kilojoules per mole of CO2. But that's not all that bad, because that gasoline you just gave me released 700 kilojoules. So let's say I'm making synthetic gasoline from my CO2, and I'm 50% efficient in doing this, so I need 1,400 kilojoules to make the gasoline. And if I'm absolutely perfect in my air capture, I need 22 kilojoules to make 1 atmosphere of CO2. And if I insist on pressurizing it, I need to double. So for 40, 50 kilojoules per mole, I can actually have that. This is tiny compared to what I need to actually convert it to a liquid. So bottom line is, in reality, everybody uses more. If you look at carbon engineering, they ultimately split calcium carbonate into calcium oxide and CO2. And at that point, you're talking on the order of 200 kilojoules per mole, because that's what this particular process wants. Now, we happen to have stumbled into a material which uses basically chemistry rather than energy to make it happen. We noticed that we have a certain ion exchange resin, Marathon A from Dow is a good example. There are a whole family of them, which can do that, that when it's dry, it really loves CO2. And when it's wet, it pushes it back off. So we pay not so much with energy, but we pay with water vapor. In effect, from the physics perspective, what happens is we are expanding water into the atmosphere, and that expansion releases energy. And we harness this energy through the features of this particular sorbent, so that at the end of the day, the CO2 gets compressed 500-fold, while the water vapor got expanded 3-fold. And you can see from this argument that clearly I need more water than I collect CO2. And so this is a moisture swing. Now, other people do a thermal swing, which works by heating up the sorbent, and then it releases the CO2. So there are various ways of getting the CO2 back off, but we all have in common that we need to put in energy, or in our case, water, to make it happen. And unfortunately, our material can get you 10% of an atmosphere or 5% of an atmosphere of CO2 pressure when it comes off. So the rest of it is conventional mechanical compressors, which have to get you all the way to liquid CO2. And for that, like everybody else, will probably pay with electricity.
So for our audience, just to back up over that a little bit, it sounded like, okay, theoretically, from a physicist's perspective, the amount of energy you have to put in is a small fraction of what you got out of the gasoline that you burned at the beginning. So that's favorable to you, right? The actual physical mechanism involves a thing which is absorbent of the CO2 when it's dry, and then you can then wet it and release the CO2 that you absorbed in it later, and maybe put
and then I have to dry it in the air.
Yeah, but then you have to pay
or heat it up.
Yeah, then you have to pay to heat it or dry.
Well, alternatively, heat it up. Then I can get my water back. But
right.
the water evaporating releases energy. Right? That's why a swamp cooler works.
Right. But if I go back to your just the original energy or dollar calculations you did right at the beginning, it seemed like you could not tolerate like if you had an efficiency which fell as low in some step of the process, which fell down to like 1% or something, you would be in trouble, right? Or in other words, if say somehow the one molecule of carbon that's in all these air molecules goes by and you just have trouble getting it, so it just kind of sweeps through. Does it sink you, or I mean?
That's an interesting question.
Yeah.
If I stand in the wind, I'm actually quite tolerant of that. If I compress the air, if I push the air with a blower,
yes,
I'm very intolerant of
yes,
that.
Exactly. Yeah.
So our particular device doesn't need to be efficient in that regard. Think of it like a mechanical tree. It has leaves, right? Surfaces which bind the CO2. What we care about is that the surfaces bind CO2 as fast as they can. We don't care what fraction we got out of the atmosphere, right? As a matter of fact, the way our design ends up working is that if there's no wind, then the air around the leaves will be free of CO2 in a short time, and nothing happens anymore. So there's no absorption. Now, if the wind starts kicking in, we get better and better and better, but then we come to the point where we saturate, right? And any more wind is really not helping us. So then our collection fraction keeps going down. And what we care about is that most of the time the wind is fast enough that we actually are in that saturated level, right? And if the wind is very high, on a day like that, we look horribly inefficient from that perspective. On the other hand, we didn't pay for the air to move. So we don't really care that the air is moving faster than we need it to, right? What we care about is that most of the time we can run, which means we are designed for a filter that works at fairly low speed. And we don't want to see so many times that the wind is so fast that it blows us over, right? And because just like a real windmill, when the wind is too harsh, we have to duck and get out of the way, right? So we like that window to cover most days. If, on the other hand, you blow the air yourself, then you don't have to worry about that, but then you paid for it, right? And now that you paid for it, you really care that you get most of the CO2 out because you already invested into the air. We didn't. So that's the advantage and disadvantage of these designs. And by the way, if you look at those who blow the air, they just barely do it just at the slowest possible speed. As a matter of fact, if there's a wind gust coming from the other side, they are in danger of swallowing this and go backwards because they can't really afford to go much past that point, which was my original. I can't go past 15 meters a second, which is still a plausible wind speed.
So for the audience, I think the way you describe the problem is a very physicist way of describing it from very first principles. And I think for our audience, it might be good if you just gave a kind of verbal description on what this device might look like. Like if you were just describing it.
We are currently working with a startup you may have seen, Silicon Kingdom Holdings, who is trying to build such a design. Probably the easiest way to think about it is to think of it as a column. There are flat disks about 5 feet in diameter, and I can pull them apart. They sort of hang on each other, and they form a vertical column when they are extended to about 10 meters tall. And the wind can now come from any direction because it's circular cross-section, so it doesn't care whether it comes from north or south or east or west. It blows in between those disks, and the disk surfaces themselves are covered in sorbent or are made out of sorbent, and so as a consequence, they bind CO2. So on the lee side of the system, the CO2 is gone. After this happened for order magnitude 20 minutes, these surfaces are saturated in CO2, and then this whole column is lowered into a drum at the bottom, which is about 2.5 meters tall, so 8 feet high, and 5 feet. I'm sorry, I'm always getting. I do things metric.
No, that's fine. Our audience can do metric.
Okay, so the thing is about 2.5 meters tall once it's closed and the lid comes down. And at this point, we are now in a position to spray water in. And one way of doing it is to first pull the air out, which is our first energy consumption. Then we have waters saturating the inside, and now it releases CO2 into this evacuated space. Then you have a low pressure mixture of water vapor and CO2, and then you have pumps moving it out and compressing it. That in a way is the simple picture, and now we can use this. Now, if you wanted to feed a greenhouse because somebody wants to just enrich that, then you'd be silly to first pull a vacuum, right? So that because you're happy to have it mixed with air, so then you make it wet with the air present, and then you blow the air from the greenhouse right through that box and back into the greenhouse, right? So there are various designs for various applications, but the basic picture is still, think of a bunch of discs, which are sort of the levels on a tree. They are rough surfaces which collect the CO2, and then for regeneration, you collapse it into a box where you then make it wet or hot if you are in a climate where it's raining all the time. If we are in a tropical climate, think Singapore or places like that, the moisture swing won't work all that well because things don't dry. Right? Because humidity is too high to begin with, in which case we would put a thermal swing material.
So one question, just to give people a sense of the comparative energetics relationship to concentration. I think for many people, the most familiar form of capture is the idea of going to a power plant and simply putting some sort of device on top of a smokestack to pull in whatever CO2 is being put out. What would be the problem of taking a device like yours and essentially attaching to some kind of flue for a power plant to try to pull the CO2 out as it's being produced? It seems like that's going to a source that's high concentration. Would it saturate rapidly? Why would it be inefficient to try your approach with much higher concentrations of CO2 in a certain flow?
You would need a different sorbent. It turns this is an interesting question. Carbon engineering and David Keith has taken the point of view you need to build things which people already understand. And flue gas scrubbing is an understood technology. And from a thermodynamics perspective, being 300 times more concentrated, of course, makes the energy penalty lower, but it's logarithmic, not linear. So we need 22 kilojoules to get to 1 atmosphere. Coal-fired power plant, if it would only take half of it out, which is silly, would end up paying 8 or so. But in reality, since they have to go down 90% and they are a little hotter than we are, they are somewhere between 10 and 15 kilojoules per mole. And so, yes, it's about twice as good, 1.5 to twice as good. On the other hand, I like to put it the other way around. If you started with 700 kilojoules, we keep 680 on the table, they keep 690 on the table. So from that perspective, it's not all that big a deal. On the other hand, if you were to use our materials there, the moisture swing wouldn't actually work. We can release at 4 or 5% even after we are fully saturated. So you already were 4 or 5% when you came in. My view is since you changed concentrations by 2 orders of magnitude or more, you have to rethink the problem from scratch. And this moisture swing sorbent, our passive technology at the end of the day, is such a specialist for low concentrations that it actually doesn't work in the power plant situation. But you can, of course, do it in a power plant with a different design and a different sorbent, right? And I think the two things don't compete. If you have a power plant, the smart thing is to get it out there unless you're in a place where you don't know what to do with it. One of my students just worked on a paper which is about to be published, where we looked at natural gas-fired power plants and said, you have a choice. You either scrub the flue stack or you instead collect CO2 from the air. And he found that in half of our cases, you are smarter to collect from the flue stack. And in the other half, it didn't work and the air capture would be better. And the reason behind it was actually, if you have a plant which has another 5 years of life, it doesn't make sense to put a big capital investment on it to scrub it. The other thing is, if your power plant only runs a fraction of the time, your capital investment is not well utilized. So basically, the paper argues that in half the cases, the plant is either too old or its utilization is too low to make it sensible. And in that case, it pays to scrub from the air. We left out in this discussion the cost of shipping the CO2, because air capture you would do where you want the CO2, whereas the power plant is where it is. And you have to have a pipeline to get the CO2 to where you want it. So, and that would tilt the playing field slightly more in our favor. But the bottom line is, in many cases, this is a smarter idea. So I view in the waste management analogy, we are akin to the street sweeper, right? And we'll take it from everywhere. That doesn't say we shouldn't have garbage bins at the street corners for people to put their garbage in, right? And so in some ways, air capture is the most expensive technology to get your CO2 back, which will be used. If you want to get CO2 back somewhere and it turns out it's more expensive than air capture, by all means use air capture. Right? If on the other hand, you have a cheaper way of getting your hands on the CO2, by all means do that. What I am arguing is there's a significant amount of CO2 we cannot get back any other way, right? And That applies to airplanes, that applies to heavy trucks and ships, and apparently at some level even to power plants. But overall, if we only get 10% of that market, it's huge. And I would argue in getting CO2 back from the environment, biomass approaches will never be large enough. Because if you are serious about dealing on the climate change scale, you can't grow enough biomass without having an enormous footprint yourself. And so I would argue, ultimately, direct air capture will set the price of carbon.
Can I ask you a kind of practical engineering / economics question?
Mm-hmm.
Suppose the world government decided tomorrow they were going to pay you something like 10% or maybe even up to 50% of the value of the energy that produced that carbon. And so, if you could get your cylinders working, that's how much you would be paid. Are you guys already there where you would just start printing money at that point? Or are there lots of engineering and efficiency issues?
Close to. I think if you look at anybody in the air capture space, SKHL included, the Silicon Kingdom company, they all shoot for the big milestone to be around $100 a ton. $100 a ton is 85 cents on the gallon of gasoline. In other words, I just take the 20 pounds coming out of a gallon of gas and say, what fraction of the $100 a ton is it? It's about 85 cents. Right? So, yes, if you gave me half the price of gasoline, I'm clearly there, right? I would argue even one step further, and I think this is one of the business models you can play in. The world, the US right now has a market for merchant CO2, the stuff which is delivered by truck, which is of the order of 8 million tons a year, and the vast majority of that is more than $100 a ton. So regulatory frameworks will have to come in if this is a waste management problem. Mm-hmm. But I could be wrong by a few years when they actually arrive, although I would make the case they are arriving right now. If that takes a little longer, there is a market you can get into, which actually is physical and exists, and you can get to a few million tons a year on that market. Now, people now talk about 45Q, which is a tax regulation, which says if you sequester CO2, you can get a $50 tax credit, so it's actually worth $50 to do that, provided you have income. And the low carbon fuel standard in California is currently worth around $180, $190 per ton of CO2. So there are niche markets. I think in Switzerland it's 90 some dollars per ton of CO2. So there are markets starting where you could enter. And my goal would be, I actually wouldn't like to see a fixed price. I would say this is a waste management problem. And I pay the company, which does waste management and is named like that, I pay money to them in order to get rid of my waste, my garbage. And notice they are not taking it because they make great things out of it, although they do some recycling. They offer me a service, and by regulation, I don't have the choice. I have to have somebody. I pay for that service because I don't have the option of saying I'd rather bury it in my backyard.
So $1 a gallon green tax on gasoline would get you guys in business, basically, if it were spent to take carbon out of the atmosphere.
Right.
Yeah, that's incredible.
And I think it'll come down from there. I would argue, I actually did a back of the envelope calculation. If you look at photovoltaics in any mass manufactured systems, the rule of thumb for mass manufactured goods is that the cost drops by roughly 20% every time you double. PV is particularly good and has dropped historically by about 24% for every doubling. Somewhere around 21% it's actually a 1/3 power law, which says that the cost every time you 1,000-fold, the price drops 10-fold. So you can now ask the simple question: if I were to subsidize you and say today it's $500, but we only do a kiloton a year, how many doublings do we need before we are $100 a ton? And if I buy the CO2 at the front end for whatever you asked for, and at the back end I sell it for $100 a ton, how much did I subsidize you? And for about $50 million, I have bought down the price from $500 to $100. So I could very well see to do the equivalent, which is done in some countries for photovoltaics, where they have reverse auctions, where they say, build me a 50 megawatt facility and I buy you electricity at X cents per kilowatt hour, and you bid on that X, and the lowest X will get it. I think you could induce a price drop to below $100. And I see no fundamental reason why it would stop there. My instinct, and it's not much more than that, is that somewhere around $30 a ton, you would really have to change the technology. And that's based on my observation that if I don't pay for our stuff, but I just pay for all the raw resources which go in, and say I need so much plastic, so much solvent, so much water, so much electricity. If I pay for all of that and pretend magic happened and it all worked, right, and I didn't pay for that, I'm coming out somewhere between $10 and $20 a ton. So my raw resources contribute $10 to $20 a ton. I'll tell you that it's very hard to make that more than half of the total. So I'm arguing somewhere near $30, you will bottom out. And that's sort of your irreducible cost. Now you may change the technology base and then all bets are off again. But at $30 a ton, it'll be 25 cents extra on the gallon. It's about a penny on the kilowatt hour for a coal plant, actually. No, a gas-fired power plant. But this becomes affordable. At that point, we don't have to argue whether this is cataclysmic to the world. We can just say, look, we managed to make a transition away from emitting carbon, and we now have a carbon neutral world. My view had always been, if the cost of dealing with it in energy terms, in CO2 terms, is $1,000 a ton, everybody will tell you climate change is a hoax. And if you tell me it's $5 a ton, people will argue, won't even argue, why haven't we done it yet? And the reality is, of course, we are somewhere in that window. And the lower we will get it, the less pain there is and the less resistance you will get to actually make it happen. I would argue that the presence of air capture will accelerate everything else, in spite of the moral hazard people who say exactly the opposite. And in a way, this is based on years ago, I listened on C-SPAN. I came late at night into a hotel and turned it on, and there was somebody from Duke Energy telling people, of course, climate change is real. We understand that. But you won't possibly want to, and I'm paraphrasing, of course, you won't possibly be willing to pay the high price of fixing this problem. If the polluter is the one who has to fix it, the polluter will say, surely I'll cooperate, but this needs a lot of research. So it'll take a long time, and it's very hard to do. If you simply can tell those people, you have a choice. If you don't want to deal it for $80 a ton, it's being taken care of by those guys, and of course you pay it. You'd be surprised how fast they can do it at 7, right? But if there is no external competition which says we can do it, I'll drag this out and I'll tell you how hard it is, because I have no motivation to add an extra cost to my system. Whereas the air capture guys are going to lobby for having more air capture, right? Because they want it, right? They are going to talk to Congress and say, we need more of this, right? Tell those coal plants to do something about it, and because they can't, right? But in reality, of course, it's easier to get it at a point source, right? So they will likely succeed if they are pushed. The other big thing air capture does is it makes storage more plausible, Because I always had this problem, storage better last 10,000 years, because nature will take 10,000 years to take the CO2 back. So if we put it all away and in 50 years from now it's coming back out, or in 100 years it's coming back out, we just push the problem down to our grandkids, right? So if, on the other hand, you have air capture, if a particular site leaks, well, then you have to pay for it a second time. And you suddenly can actually monetize this on day one, because you can ask for insurance. And the insurance will pay guys will pay attention that you actually did it right, because otherwise they are on. Right? So suddenly the simple ability that you can put a money amount on it because you know what it costs to capture. Right? But before that, people will say, well, we put it away, and if it gets lost, then we'll say, oh, well, we didn't see that coming, and sorry about that, but there's nothing we can do. But if you have air capture, you can close that cycle. You can also talk to countries in the developing world and say, you are not yet at a stage where you really can afford it, but frankly, your emissions are a few SUVs in this country, and we'll take care of it on your behalf for a decade or two. And then it's your job. It just adds flexibility to the system.
When you talk about permanent capture, what do you have in mind exactly? You're not simply pumping it into reservoirs underground.
You mean storage?
So what?
Well, I got into this via mineralization, right? When I started, I felt the really hard part of the problem is not the capture, but the storage. And it's not hard to store a little bit of CO2. If you tell me how to get rid of a ton of CO2, I say, well, there's a gazillion ways of doing this. If you say, well, it's 1 million tons, it's still okay, not a big deal. At 1 billion tons, I'll say, I'll take a deep breath, but we'll figure that out too. But we are really talking about 1,000 billion. We're talking about 1 trillion tons of CO2, which are in play here, right? We are currently putting out 40 billion tons a year, right? So over a century, this is 4 trillion tons of CO2. So that's the order of magnitude for storage. And I felt your best option is to turn it to carbonate. But in the short term, there's plenty of geological storage capacity for injecting it into reservoirs. And there are plenty of saline aquifers all over the country, all over the world, which could probably hold most of it. We can argue whether that's really true, but for the next 10 years, we are not running out of capacity. So I like my mineral carbonization, don't get me wrong. And I think in the long run, that's the right thing to do. But in the short term, we actually have no excuse that we wouldn't know where to put it. Right? And the oil companies have developed these technologies for enhanced oil recovery over decades. They know that they can do that. And so, yes, there will be a lot of NIMBY and NUMBY, not under my backyard, but...
So, Klaus, I want to be very specific here. Where are there large enough reservoirs to put them? Are they under New Jersey? Are they in Niger?
Yeah.
Or are they...
They are not in New Jersey. They are closer to where you are. Basically, under all the sedimentary basins of the world, deep saline aquifers. Sometimes they are actually not deep saline aquifers. They are filled with oil and gas. And you can use the same type of reservoirs to put in CO2. In the North Sea, Equinor now, Statoil in the past, has put 1 million tons of CO2 a year into a single well. And they have done this now since 1996. Right? And they claim that that particular formation, the Utsira formation, is large enough that it could take basically all the CO2 from Central Europe for the next 100 years or so. And that's one huge aquifer, admittedly a very large one. And that has been working just fine. In the IPCC report from 2005, they claimed that you could put 4,000 gigatons into the aquifers in Alberta alone. I disagreed with that number for another reason, because it would raise Alberta Alberta by 6 meters. But I do get the point that you could dissolve that much CO2 into those aquifers, right? And so my point is there are plenty of them. In Iceland right now, CarbFix is injecting CO2 into basalt formations. And they have made a very good claim that actually forms solid carbonates underground in a matter of years, not decades. And so you could very well end up in a situation where you say we can put CO2 away, forming carbonates underground in basalts. If you look at basalt formations in the world, they're huge and everywhere. And what you see in Iceland is basically an extension of the mid-Atlantic rift. So you could do this basically all up and down the mid-Atlantic and conceivably put vast amounts of CO2 away this way. Keep in mind, we got the stuff from underground, right? So it's not that there's not enough capacity to put it, but I also can see that in the past we drilled a lot of dry holes when we looked for oil and gas. In the future, we will drill a lot of leaky holes where we try to put it in and saying, this is really not the right place to do it, and where exactly your real capacity is, only time can tell. But if geological storage is not right, you can still do mineral storage. The mountain range in Oman alone could take more carbon than the world has coal, oil, and gas.
And how would you go about pumping it in there?
In Iceland, it's a little unusual because they don't have a capped rock. So they actually dissolve the CO2 in water before they send it down. And that requires an unusually open formation because otherwise the energy it takes to press it in would be too much, but they can do it. And presumably you could do this all along the mid-Atlantic ridge. And there you clearly have water. So one of the things they now have to demonstrate that salt water will be as good as fresh water. And in my view, they have to demonstrate that the capacity down there is actually as large as they hope for. All they know is that at the small amounts they put in, it really works. Now the question is, if you put in 1,000 times more, whether you simply run out of capacity or not, and only time can tell. But I would argue if you take all the options you have on the table together, we are not running out. As far as cost is concerned, most of these options are probably cheaper than the air capture on the other end.
Are there ecological consequences to it? Negative ones, aside from raising the ground level?
Well, you don't want to get to that scale, right? But this is what happens if you say, I'm checking for one parameter and it basically says there's no limit. We could put 4,000 gigatons. I said, okay, what's the volume of 4,000 gigatons? And how much height would this imply? And I end up raising the ground by 6 meters. So clearly we overdid it, right? On the other hand, Alberta doesn't have to take 4,000 gigatons. Well, you clearly have some impact on the formation. Its chemistry has changed. The risk is that it comes back, right? And CO2 could come back catastrophically. On the other hand, enhanced oil recovery has taken this risk for decades and managed it quite well. Right? That risk, in my view, is tiny. The more likely concern is that you come back in 100 years from now and you say, well, it's all gone and we don't know where it is, right? In which case you have to pay for a second time of cleaning it up. But even that risk is very, very tiny. I think in the end, people have made a strong case that most of these reservoirs will hold that CO2 for tens of thousands of years. On the other hand, we have never done things on this scale. And people have worried about seismic activities, right? You think Oklahoma, people taking wastewater from fracking and inject it deep underground and have triggered seismic activity. My friends in reservoir engineering say, of course, we would never put it there. That may be true, but the people who put the water there also didn't mean to create seismic activity. So I would argue, and we made ourselves horribly unpopular some 10 years ago when we wrote a paper where we argued you actually should define what will happen. And if the actual course of events deviates from it, you have to take the CO2 back out. And given that you have air capture, you can actually afford that. And in doing so, I think what the likely outcome is that 99% of the reservoirs you put it in are just fine. And you are managing that last percent, and maybe we are talking 2% versus 1%. But reservoir characterization then becomes critical. And in hindsight, it's quite clear that the Oklahoma wastewater disposal was in the wrong place. And you can actually tell why. And this is not a typical situation for an underground reservoir.
Are we almost out of time?
I think we're close, but at least
Okay,
go ahead, Steve.
Well, okay, before we run out of time, I wanted to ask Klaus a question on a totally different topic, which is that I saw that he had done postdoctoral work with George Zweig. And
Yes.
I'm curious, so Zweig is a very well-known guy in particle physics, and in fact was one of the people who proposed what now we call quarks. He called them aces.
Yes. He called them aces.
Yes,
I remember.
and so I'm just curious if you had any stories about George, because he later went into sort of neurobiology, and then I think he worked at Renaissance, which is a quantitative hedge fund, for a while. So
Yes.
a very interesting guy, and I'm just curious if you have any good stories about George for history's sake.
He was an interesting guy. I ran into him at Caltech as a postdoc, and we started to work together on what would happen to the chemistry of an atom, fractional charge embedded into its nucleus. And he went at that time to Los Alamos, and the reason I ended up in Los Alamos was him, because I was at Stanford working on the phenomenology of weakly interacting supersymmetric particles. And George, one night, we were still working on papers together, asked how I like it. And I said, well, the problem is nobody can prove me wrong for the next 200 years. And he said, do you really mean that? And I said, yes. And 2 weeks later, I had a job offer from Los Alamos with the explicit stipulation that I cannot join the particle physics group. And that was George's doing. And so...
Does that mean you weren't in T8? Were you still in T8, or?
No, I was in T dot.
Okay.
What is T8 and T dot?
T dot was, he was in it too. T dot was all the people you didn't quite know where they belong.
T8 was particle physics, and
yeah, T8 was particle. For a long time, I was T3, so I was in fluid dynamics, and George was trying to get me into the physics of hearing.
Would you say you've been sort of moving away from? So you started with very, very fundamental physics, and now you're doing something very applied and important in the environment and technology. And can you just reflect a little bit on the journey?
Well, it's probably a trend that I consistently got interested in the importance and applicability. And on the other hand, I think having a good theoretical background is actually incredibly helpful. And I would actually point out that a number of the people in direct air capture all came out of physics and not out of engineering. And I think I understand why, because engineers get trained to be careful. Physicists don't. And so physicists are more willing to jump outside of the box and say, on first principles, there's nothing wrong with it. So now let's figure out that it really can work. And one of these struggles chemical engineers have, first they argue that thermodynamics doesn't work, but it's easy to convince yourself and even a chemical engineer that that's not a problem. But then there was Sherwood's rule, and the great Sherwood, who was a chemical engineer in the 50s, had said, the cost of separation is roughly linear in the dilution. And since we know what it costs to scrub a power plant, which is somewhere between $10 a ton if you're an optimist and $100 a ton if you're a pessimist, multiplying that by 300 is, of course, devastatingly expensive. And I would point out that Sherwood's rule is already broken if you look at what Kleinberg's carbon engineering everybody is doing right now. So it doesn't apply. But I was curious about that before I started into air capture. And I said, why do you have a rule like that if you know that the thermodynamics is logarithmic? And I finally realized that what Sherwood had looked at was metals in ores. And the multiplier in there, the proportionality constant, is $10 per ton of rock. So basically, the cost of a metal is $10 per ton of rock it came from. So if it's 0.1%, then it's $1,000 a ton, and if it's 0.01%, then it's $10,000 a ton. And what struck me back then was, okay, if I have $10 per ton of rock, what can I actually do for it? Well, I can dig it up and crush it. That's about $1 or $2. I can crush it and grind it. Now I'm at $4 or $5. I can run a flotation to separate good stuff from bad stuff. Now I'm at $7, $8. And I can get rid of the tailings. Now I'm at $10. So basically what Sherwood's rule says, the first step of contacting everything is of course linear in the dilution. And if that dominates your cost, then you have Sherwood's rule. But what if it doesn't dominate your cost, right? I'm not crushing and grinding air. As a matter of fact, I went out of my way, not even blowing the air around. So then it's the second step which dominates the cost. And that's driven by thermodynamics. So I'm arguing
Was getting past Sherwood's rule among these engineers a 5-minute conversation, or was it a 5-year conversation?
Probably closer to 10.
Okay.
It nearly killed us. Read the EPS report, right? And I back then didn't get it. So people said, if you were to do this brute force with a technology, which I, by the way, estimated to cost $10,000 a ton at $600 a ton, this is devastatingly expensive and we can't do it. And I said, I couldn't help myself. I looked up that after this, I looked up the Tesla Roadster, and I worked out how much money you spent on batteries to avoid a ton of CO2 coming out of the tailpipe of that Tesla. I'm not even arguing whether it came out of a coal plant or not. I just give you that it didn't come out of a tailpipe. Turns out it's $600 a ton. Now, today's Teslas are much, much better than that because you came down with winning. So I took the $600 for that first thing as the glass is half full. They took it to mean half empty. And coming down a learning curve is actually not all that unusual, right? And photovoltaics today is 100 times cheaper than it was in the 60s. Wind is about 50 times cheaper. And in the 20th century, the price of a lumen of light dropped 7,000. Right? So, yes, the first time around, these first prototypes would be horribly expensive. Right? But I think that's manageable. Right? You've got to come down the learning curve. And there are enormous things you can learn. Whether you look at computers, if you look at cars, one of the things which really changed my mind about a lot of things is the observation that a car engine is $10 a kilowatt. Your average coal plant is about $1,500 a kilowatt. So mass production really can change the game. And so I don't see us building larger and larger units. I see us building containerizable units, which are being factory delivered and plonked down where you want them. And if you want to go to 40 gigatons a year, which is not a bad number to aim for, you need about 100 million. Right? But if they last 10 years, you need to build 10 million a year. We built 90 million cars and trucks a year. So those numbers are large, and that's not surprising because you want to solve a very, very large problem. But on the other hand, they are not of scale large for human industry. Actually, Shanghai Harbor exports about 30 million shipping containers. Right? So if these are like that, Shanghai has an export capacity behind it, which is 3 times larger than the whole world would need to deal with the CO2. If we want to do it, we can do it.
Yeah, and very few of those containers come back. It's a kind of one-way flow of containers from China to the rest of the world.
Right, but it shows the capacity to operate on that scale exists.
Yeah, and there are that means there are a lot of containers for you to use for your containerization.
Sure. Yeah, I actually years ago looked at that. For $3,000, I can get a shipping container.
Yeah.
And ultimately, that ton-a-day device has about a $30,000 budget. The first ones will be a few $100,000, but if you want to talk $30 a ton, you better have that shipping container at about 30,000, which is not all that far off from where a car is.
Well, thank you, Klaus, for taking time. This has been a really excellent conversation. I've learned a lot.
Yes, I think our listeners will enjoy this quite a bit. Thank you very much.
Okay, you're welcome.